Can you hear me all right?
Otherwise we always hear.
Okay.
Yes, we can.
Okay, good. Okay, everyone. So it's our pleasure to have Lars Lindemann as a speaker here. Lars is currently a postdoc at UPenn, working with Professor George Papas on control theory, learning theory, and risk-sensitive control. He's done some great work on optimal control, path planning for robots with risk awareness, and he will be starting as an assistant professor at USC next fall. So, without further ado, please go ahead.
Yeah. Hello, everyone. Thank you for the introduction. I hope you can hear me fine on Zoom. I'm really excited to be here in person, to interact finally again and to present my work. I'm not going to talk about control today, though. I thought it's a nice complement to talk about risk verification. Okay. So in particular, I want to think today, or we want to think together about new and principled ways how we can kind of quantify risk in autonomy and robotics by using elements from formal methods. Okay, so we really want to conceptualize risk in a kind of different way. And I will then try to convince you of the usefulness of these new notions of risk by verifying AI-enabled systems such as self-driving cars in terms of their risk. Okay, so this is the agenda for today. Okay, my pointer doesn't move. First off, what is risk? I mean, we got a good overview today, and I think everyone has their own definition of risk in mind, but I think there's really no commonly agreed upon notion of risk, right? And that's why we meet here today. However, risk always involves uncertainty and the probability of, failures. For instance, if we talk about these or if we look at the bipedal robots over here, risk may measure the likelihood of a failure, right? In autonomous driving, however, risk may measure the cost of a collision. It's a different interpretation, right? If we talk about sensing and perception, we may have risk maps that indicate risk-free paths. So another interpretation. And in learning, risk has recently been proposed as an alternative to minimizing over the average loss, right? But how do we define risk when humans are in the loop, right? My point here is that risk is always a matter of definition. And my first objective for today, and I think the objective of this workshop, is really to establish a common language to talk about risk and to conceptualize risk in robotics. And I particularly want to do this by bringing in elements from formal methods. Okay. My second objective for today is to then use these new notions of risk to verify AI-enabled systems in terms of their risk. So in brief, what is system verification? System verification algorithms simply check if a system satisfies a specification. So like I said, we are not designing controllers here today. The way this works is typically you have a system like a car over here, a specification. For instance, you never want to collide and avoid jerky control behavior. You abstract specification and system into a discrete domain. Typically, you use a verification algorithm that will tell you whether or not you satisfy the specification. Okay. Now, the question is, why do we want to verify autonomous systems if we can design them in a safe way, right? Well, I mean, most likely, if we design any algorithms, we do this under nominal conditions. However, if we put a system into the real world, there's always uncertainty in our model, in the environment, and several other things in the data that we get, right? Here, for instance, we have learned a control barrier function that is safe, but as soon as we put noise into the system, we get jerky control behavior. But more generally, modern AI algorithms really don't provide any safety guarantees. Here's a vanilla imitation learning approach that if we apply it in the simulator, it is definitely not safe and will even collide. And we also know by now that AI algorithms, specifically neural networks, are really not robust, right? So we're sensitive to input-output or input variations that may result in large variations in the output, which is especially harmful for us when we talk about perception, okay? So these are all good arguments why we would also like to verify our systems. And the question I'd like to ask is, can we quantify the extent of safety and can we measure risk? Okay. And this is supported by, for instance, statements by the National Transportation Safety Board here in conjunction with an Uber accident a few years ago, where the reason for this accident was stated as Uber's inadequate safety risk assessment procedures. And they state the need for safety risk management requirements for testing automated vehicles on public roads, right? And this has also arrived in the scientific community. I guess that's why we're having the workshop here today, right? Existing verification techniques, I want to mention them briefly. They are more coming from the computer science domain, and they are really powerful, but they do not necessarily assess risk the way we want to do it today. There's exhaustive testing, but this, of course, is by no means systematic. There's a huge body of literature on model checking and deductive verification. However, here modeling is crucial, why we would like to rely on data here in this talk. And they also don't assess risk. And there's statistical model checking. And while this type of literature assumes to have data at hand, there's no use of mathematical risk in the way we want to do. So in summary, the objectives for this talk are first to conceptualize risk in robotics using elements from formal methods. And like I said, to then use them for system verification. Okay. I now want to introduce my definition of the risk of failure. And I'm going to give an overview first before I zoom in into the details, all right? Now, in order to talk about risk, we can use risk measures, or as Margaret called them, risk functionals. And I'm just going to repeat them real quick. Let's assume we have a cost distribution over here. Then one risk measure is the expected value or the worst case simply, right? We're here particularly interested in tail risk measures, such as the value at risk, which is the 1 minus beta quantile, or the conditional value at risk, which is basically an expected value over this quantile, okay? Why are we now interested in tail risk measures? Why don't we use the expected value? Well, simply in that case, we would probably get very good average performance, but we wouldn't be safe, right? Now, if we're interested in safety, why are we not simply using the worst case? Well, if we look at autonomous driving, if we want to avoid the worst case, we shouldn't just be driving, right? So in order to get from A to B, we need to be willing to accept some risk, and we need to be talking about tail risk measures, basically, which give us a good tuning knob between average and worst case cost. Okay, so how do we now define the risk of failure? Basically, the idea that I'm following here is to quantify the risk of lacking robustness against failure. So I'm talking about robustness here. And the reason why I'm doing this is that failure is often caused by lacking robustness against modeling uncertainty, against uncertainty in the environment, or even uncertainty in the data generating process, right? We've heard about distribution shifts today. And I'm going to use two notions of robustness here. I'm going to use spatial and temporal robustness. Just pictorially, what is spatial robustness? It's, for this example, where the blue car wants to overtake this black van, it's the maximum size of a tube that we can put around the nominal trajectory without intersecting with a car, right? So we're thinking in terms of tubes over here. And in fact, since we have stochastic systems, we may have different realizations, different robustness values, okay? And the point then is that these robustness values, they map into a robustness distribution over which we will define our risk. Now, spatial robustness is useful when we're interested in distances, like safety distances. But I'm going to argue that temporal robustness is equally important, especially if we're talking about multi-agent systems. Let's say we have several agents that are involved, and there's timing uncertainty. One agent may be delayed, one agent may be arriving too early, or there's even a human that induces timing uncertainty, right? So we should also be interested in temporal robustness. Here, a simple example, we want that the service is enabled within the time frame. Then temporal robustness for this specification is simply the distance from the time the service is enabled until the closest deadline. The same story repeats. We have different realizations here, different temporal robustness values, and they map into a robustness distribution, okay? And then we can define the risk of failure as follows. We pick any risk measure, could be the value at risk, conditional value at risk, really any risk measure we've talked about today. And we wrap it around the negative robustness. And robustness can either be temporal or spatial robustness. Now, why are we using the negative robustness? Simply because risk is traditionally defined over a cost, and the negative robustness is just our cost, right? And this captures the risk of lacking robustness against failure. Okay. So far, we have talked about risk and robustness. I, in the beginning, said we're talking about principled ways. And the reason why I was using the word principled is because we can use temporal logics as a specification language, okay? And this will allow us, especially for robotics, to use it as a general way to express system specifications, okay? So we can express broad classes of specifications, and everything that I'll be showing afterwards can be applied to such specifications, okay? But I'm not gonna go in detail there. What temporal logics are is basically Boolean logic equipped with temporal operators, such as eventually, always, and until. And one specification, for instance, that we can impose for a drone is that the drone should always avoid region E, every hour inspect regions A and B. When the battery level is empty, it should recharge in C or D, and always between a certain time, the communication should be turned on, right? So these are the types of specifications we will be able to consider, over which we will be able to define robustness and hence risk. Now that we've talked about this, I'm going to give you an overview of the risk verification framework just in pictures. We're assuming that the environment and perception, as well as the system and potentially learned controllers, as well as disturbances, are all modeled as stochastic systems from which we assume that we can draw data, okay? So we can simulate this system. At the same time, we're assuming specifications such as safety and performance, and we're feeding both of these things into our risk estimation algorithm, from which we estimate the risk of failure, okay? So this is the high-level overview. I want to zoom in a bit now and talk about the spatial robustness risk. And this is again motivated by safety critical applications such as cars or drones, where distances are really something that we're interested in when talking about safety. All of these autonomous systems, they really rely on SLAM techniques to localize themselves in its environment, right? And we're using LiDAR, radar, cameras for this purpose. And naturally, we introduce estimation uncertainty there. We may have also modeling errors that may cause tracking errors in our control, right? So safety really hinges on spatial robustness to such uncertainties and also on risk awareness. So how can we formally capture this? And I've before used this picture of tubes, and we can formally define them basically by taking the distance of a signal X to the set of signals that violate the specification, okay? It's a simple distance to a set, and this will give us this tube. And in fact, it holds that if this distance, this robustness degree is positive, we satisfy the specification. And if it's 0, it means that we violate it. So while this is a really nice and neat interpretable definition, it's hard to compute. But what exists there, and I'm not going to give a definition, but there are robust semantics that you can calculate in closed form. And these robust semantics here in red, they under approximate the tube that we have. So instead, we're working with a smaller tube that will still give us robustness, okay, as a way of quantifying robustness. So we're using this red notion from now on. And then we define the approximate spatial robustness risk simply by putting a risk measure around the negative approximate spatial robustness risk, right? That's what we talked about before, which captures the risk of lacking robustness against spatial uncertainty. Just as a small example, let's say we have a capacitor that discharges over time, and our specification here is that after 2 seconds, we want that the capacitor has discharged below 1 volts, right? Let's say we have collected a bunch of data, and we have plotted a histogram over here of the negative robustness. Then what we would do is we would calculate, for instance, the value at risk at the 1% quantile or the 5% quantile, right? And the interpretation then is the following, that in 5% of the cases, we have a robustness that is lower than 0.6. And if we then have modeling errors, this can tell us something about how safe the system really is under this additional modeling uncertainty, okay? A nice property that we have is if the risk measure R is monotone, which is a property that holds for most of the risk measures, then we have that our approximate spatial robustness risk is an over-approximation of the risk we would obtain when using this robustness degree that, however, is hard to calculate. Okay, next question is, of course, is how can we exactly, or can we exactly calculate this robustness risk? And the answer is no. But we can estimate it from data. And I'm going to show you how this works, for instance, for the value at risk, but you can do it for other risk measures as well. The way we do this is we assume that we have observed n system trajectories, right? So we get n spatial robustness values that we denote by Z1 to Zn, and we assume they're sorted in an increasing order, okay? And then we're basically using a result from Dionysus, who is going to present after me, which is really nice and gives us upper and lower bounds by simply picking the z, the n times beta plus gamma largest and the n times beta minus gamma smallest value, where gamma is basically the square root of 2 log of 2 over delta. Delta here is a failure probability, and then again over 2n. And then we know that with a confidence of 1 minus delta, we have obtained upper and lower bounds. So it's really easy for us to get upper bounds that we're interested in. Okay, so let's look at a case study. We have an autonomous driving simulator here, and we trained 4 controllers, 2 imitation learning controllers, one with full state knowledge, one with partial state knowledge, and 2 control barrier functions with full and one with partial state knowledge. The partial state knowledge controllers here take images from which we estimate the position, okay? And as you can see here, the controllers are doing, well, some are doing good, some are not doing good, but we want to verify now how well they're really doing. And for that reason, we're calculating or estimating the spatial robustness risk based on the cross-tracker. Now, the cross-track error is nothing complicated. It's simply the distance of the car to the middle of the road. Okay, so this is the quantity we're using here for this verification. First specification we're looking at is safety. We want that this cross-track error is always below a threshold for 2.25. Okay, so here are some trajectories and the histograms of the negative robustness values, and we see that the partial state knowledge controllers in green and red, they perform really poorly. They, in fact, have a very high risk, and we will neglect them from now on. However, when we look at the full state knowledge controllers, the imitation learning controller in blue and the CBF controller in yellow, we see something interesting. Here, the expected value, so the average risk of the CBF controller is the lowest. However, it has a tail of non-robust realizations over here. And this is reflected in the fact that the imitation learning controller in blue has a lower value at risk. Okay, so we can use the value at risk here to detect the least risky controller when we look at safety over the whole trajectory. However, the question is, why is the CBF controller performing better on average? And in order to find this out, we're going to look at safety now in steady state. So after 10 seconds of the controller, after 10 seconds that the controller has been running, and steady state, so really when the car starts moving. In steady state, basically, we look at the same specification, the same cross-track error below 2.25, but only after 10 seconds. And now it happens that the CBF controller suddenly is the least risky one, both in terms of expected value and value at risk, okay? And this kind of means that actually in the transient, the CBF controller must do a poor job. And this is what we see when we're looking at this specification, the same one, but we want that it holds within the first 5 seconds for 5 consecutive seconds. We see that the imitation learning controller performs better, is less risky than the CBF controller, okay? Just to summarize this, I have picked one realization of our simulator. The CBF controller in the beginning goes way over the line. So the controller is doing a poor job in the very beginning. But as we're transitioning into the steady state, which happens after 10 seconds, so now, we will see that the CBF controller is performing better. In fact, in a few seconds, you will see that the imitation learning controller here goes over the line, so is not keeping the car within the lane, which the CBF controller does. And this is what you see if you look at a lot of realizations and what we just estimated from the risk. One thing I want to briefly talk about, I'm not going to spend too much time on it. What we've done is we've calculated risk in a simulator, right? And let's say this is gamma. What can we say about risk on a different course, right? If we're doing a right turn, or what can we even say about risk in the real world, right? And this is where I think robustness can come in handy, because it can give us upper bounds. Basically, we can get upper bounds on the risk, for instance, on the test track, from the risk on the training track, right? And what we show is that basically, if we can bound the distance of a nominal and a perturbed system, let's say by delta, then this will imply that the risk of the perturbed system is upper bounded by the risk of the nominal system exactly by this delta. So the kind of trajectory difference will exactly show up in this risk bound as well. So how do we get delta? I'm not going to go into details. We can use Lipschitz constant, can be conservative and is restricted to some systems. If we have incrementally input to state stable controllers, this will give us such bounds, or we can estimate it using statistical tools. Okay, how much time have I left? Okay, so I'll quickly rush through this. temporal robustness risk, like I said, is motivated if we're talking, if we're interested in timing uncertainty, right? Such as in time critical systems. So these are systems in which meeting stringent real-time constraints is really of major importance, such as in air traffic control systems, autonomous driving, train scheduling, or automated warehouses. Like I said, it's important in connected systems, and failing to meet these real-time constraints can jeopardize the safety of the system. So now, what may be reasons to fail to meet real-time constraints? If we're looking at network control systems, there may be delays in the computation, communication, actuation, and sensing, right? On embedded hardware and computation, we may have delays in scheduling. In connected systems, we may have various delays in traffic participants in this case. In fact, Elon Musk stated with respect to autonomous driving that if you have a stack up of timing tolerances, then you can have a variable latency, which is called jitter, and which can really make it hard to anticipate how to turn and accelerate the car, right? So in summary, robustness against timing uncertainty is really critical. But the question is, how can we analyze and define temporal robustness? And I want to introduce the two notions of temporal robustness that we have on a simple example. Let's say we have a two-dimensional signal x that consists of x1 in red and x2 in blue, okay? And our specification is we would like that the difference between these two signals is always below 1, between 145 and 155 seconds. So in this green box, okay? Then we can define the satisfaction function, which is 1 if we satisfy the specification, and -1 if we violate it. So basically, the indicator that you should keep in mind is if this black curve here is below 0, the specification is violated. Okay. First, we define the synchronous temporal robustness, and the idea there is simple. We just shift the whole signal to the left or right until we violate the specification. If we shift by 5 time units, the specification is still satisfied. So let's shift a little more. 12 time units, we still see the specification satisfied. But if we shift by 13 time units, we violate the specification. And it turns out in this case that the synchronous temporal robustness is 12, meaning we can shift by 12 time units to the left and to the right without violating the specification. Formally, we say that the synchronous temporal robustness eta is basically equivalent to the maximum individual time shift for which we still satisfy the specification. Okay. Now, this is a really simple definition, right? And what I said before is we're more interested in asynchrony, right? If we have several agents evolved. And therefore, we define the asynchronous temporal robustness where we shift the signals x1 and x2 independently to the left or right, so asynchronously, until the specification is violated. In this example, if we shift by 1 to the right and the blue signal by 1 to the left, we see we still satisfy the spec. If we shift a bit more, we still satisfy it. But once we shift by more than 4 time units, we will violate the specification here. And in this case, it turns out that the asynchronous temporal robustness is 3. So we can individually shift both signals to the left or right by up to 3 time units. Okay, and we can again formally define this as the maximum individual time shift while still satisfying the specification. First case study here is a T-intersection. We have a Boolean specification. This means nothing more that whenever the green car is in the middle of the road, it should have a safety distance of at least 15 meters to the blue and the red car. And here on the left-hand side, you see the scenario when no car has a delay. On the right-hand side, you see the scenario when the green car starts 12 seconds too early and the red car starts 12 seconds too late. And what we see then in this case, due to the delay, simply that the specification is violated. When the green car is in the middle of the road, the red car is really close, kind of violating the safety spec. And the asynchronous temporal robustness is 11 here. Since we shift by 12, we violate it. Another one I want to briefly mention is for a temporal logic specification. Roughly, it means that both robots should recharge in the charging area for some time. They should eventually gather in region B, and they should periodically visit region A over here. So a more complex specification, the sub-specification you see here, and they're satisfied when the signal is green. So we're recharging both robots. They're going to meet in region B and satisfy all of their specifications. Now, the synchronous temporal robustness is 7. If we shift both robots, if they start both of the robots 8 time units too early, we see that we violate the charging requirement of the second robot. It will not be sufficiently long in the charging area. The asynchronous temporal robustness here is 6. So if we let robot 1 start 6 time units too early and robot 2 7 time units too late, we see that both robots will not have their rendezvous in region B. So they will be shifted in such a way that they can't complete their collaborative task in region B. You see basically here when robot 1 leaves region B, robot 2 will be about to enter. Okay. Now, these notions are defined for deterministic signals. In reality, of course, we always have stochastic systems. We have some noise on top, right? So here, in this case, the velocity of the cars may be subject to some noise. So if we draw, let's say, 1,000 or 10,000 realizations, we get, again, a distribution of temporal robustness values. And in the same way we defined robustness, the spatial robustness risk, we're defining the temporal robustness risk by using a risk measure and putting it around the negative asynchronous and synchronous temporal robustness. Okay, I guess I'm running out. Oh, okay, then I was hurrying for no reason. Okay, so this is the risk of lacking robustness against timing uncertainty. So first case study here, we just assume that the initial time of each car in this T intersection scenario is uniformly distributed within minus D and D, and D is a maximum permissible time delay that they may have. We calculate the valued risk at the 5 and the 2% quantile, and naturally we see the more timing uncertainty we allow here. So as we go down these rows, the higher the risk will be. Okay. We can also see that the estimates are tight. So when we compare columns and upper and lower bounds, we see that the estimates we get are really tight. We get good information basically, and these estimates also tell us how much more timing uncertainty we can sustain. For instance, if we're looking at the first row over here where we are not allowing any time delay, we have a risk of -10, and we can use this to upper bound the risk when we have a delay of 10. In fact, the bound we get, the theoretical bound here, is 0, and as you can see from the experiments, this is kind of respected. The last case study I want to show here is basically the scenario we saw before, scenario 1, and basically scenario 2, where we flip the velocities of the red and the blue car. Okay, and we want to use risk measures to compare which of these scenarios is more risky. In fact, something interesting happens if we look at the 15% quantile. It holds that scenario 1 has lower risk, while if we look at the 5 and the 2% quantile, scenario 2 has lower risk. Okay, and this is what we also see when we plot the histograms. Basically, the mean, in a way, of this blue distribution of S1 is lower. However, it has this tail of non-robust realizations, right? That may be important when we're talking about timing uncertainty. In fact, here it goes even positive, which means that the specification is violated. Okay, and by that I would like to conclude. These are some references, the main collaborators that worked on this. I also want to do some self-advertisement. If you know someone who is interested in PhD positions, please forward them to me. Thanks.
Thank you for the talk. I guess we have some time for questions.
Thank you for the presentation. Just wanted, I know you said you would avoiding controls for this specific talk, but have you done any work? Like obviously, if you had a control system there that could recognize that there was a risk, it would change its trajectory.
Yeah.
Is that currently being utilized in your?
Not in this work. So I have worked on risk-aware control, but there the objectives are more simple. If you put temporal logics in the loop, they have a formal syntax and semantics that consists basically of a lot of nonlinearities, then control becomes more difficult, let's say. And this is something I'm looking into now. But you're completely right. I mean, as soon as you change the control action, the underlying distribution will change, right? So then the kind of data that you got before is not maybe useful, but you need to account for shifts. And there the robustness may come in handy, right? I mean, if you have some robustness in your definition of risk, this can potentially account for these distribution shifts that may be caused by changing your control action. Point being is, if you verify a system, let's say in a simulator, right? you want to go from a simulator to the real world. And you verify, you have 5 controllers, right, in a simulator, and you find a controller that has the lowest robustness risk. We can also show, I haven't shown this here, that if we move to, in this case, a more realistic setting, not to the real world, then you can observe that this robustness helps you translating to the different setting, adapting to the distribution shift due to the robustness that you have. So it kind of gives you a buffer to these kind of things. But I haven't actively been doing control in this way, under temporal logic specifications. If that answers the question. Yep.
Any other questions? Okay, I have one question. Much earlier in your presentation, you speak of this robustness function, which is you kind of wrap your objective function with another R function, and you say, well, this is now my robustness function.
Mm-hmm.
It wasn't very clear to me. What is this function? Like, you spoke of many different robustness ideas throughout the presentation, but it wasn't really clear to me how do these functions map back to the main objective function that you wrote in your earlier presentation.
Wait, let me maybe go there. I'm stuck here. Are you talking about this basically?
Yes.
Okay.
So you basically say I have this risk measure and I have my robustness function, and then when you proceed in the presentation, you speak of different robustness criteria, but it wasn't very clear. So do you augment all these functions, or depending on whatever scenario you have, you pick?
Let's say you have a system X, okay? And you have a specification phi.
Okay.
That is your temporal logic specification, something complex. Go from A to B, avoid a certain region, right? Then you can basically obtain in close, you can just calculate based on a trajectory what robustness this trajectory has with respect to a certain specification.
Okay.
And you can either talk about spatial robustness or temporal robustness.
Okay.
Okay. And then it depends on what you're interested in. Are you interested in spatial robustness or in temporal, or maybe in both? But the point is, for one realization, for one trajectory, you will get a robustness value with respect to the specification. And since you have a couple of realizations, you will basically get a distribution. Okay. So all of this minus rob of phi of x will be a distribution. And that's why you can define the risk over it.
That makes a lot of sense. Thanks a lot.
Yeah, I should have maybe spent a bit more time.
So now we have a lot more questions.
Okay.
Hey, Lars, great talk. So I guess in all of this, you're assuming that you've been given a temporal logic specification, but oftentimes these specifications can be written down by a human and they may be prone to errors. So I'm curious if you've thought about robustness to LTL misspecification.
Not in this work, no. No, I have not just briefly discussed it, I guess, with colleagues at some point, but not really. So here it's really, you get a specification from a human user and you just assume that's exactly what that person wants to know. Yeah.
Do you have any thoughts on how you might be able to incorporate that? In
this framework or in general?
Or in general.
I was thinking for a while about distances between formulas, if there's such a thing, if that makes sense. But I don't really know how you would define it in the end, distances of formulas, because it seems like you could define it in many different ways.
And it should also somehow be, it should also depend on the humans, I guess.
Yeah. But it would be something like, this time interval is given, but what the human really means is something larger or smaller. Same for predicates, same for, you could also think about, what is, if the human means an always, but gave you an eventually or something like that, because or some semantical errors.
Yeah, it seems ill-posed, but okay.
No, I think that's an interesting question, actually. I haven't seen anything on that. I think related is like formula repairs.
Right. Yeah, I've seen some of that. Cool, thanks.
Take one more question.
Mine's a short one. So just a clarifying question. Are you using like two different formal languages? For spatial, is it linear temporal logic? For temporal, it's LTL, and for spatial.
It's the same temporal logic.
So STL can account for both of them?
It's the same temporal logic. So you use STL, and you can, for the given specification that you have, you can calculate a spatial robustness value or a temporal robustness value or both. So these are kind of, you have your semantics or your syntax, your semantics, and then you put spatial semantics or temporal semantics on top. But
Okay.
you don't change anything on the way you define your logic.
So the semantics where you can, the robustness value is always greater than 0. Is it something that you defined, or is
So the deterministic version is something that is out in the literature since 2009, I think.
okay?
It's for spatial robustness. Temporal robustness is something newer, I'd say. There aren't that many works, and it's more like, I think people are starting to get interested in it for various reasons. I mean, if you have connected systems, that's something obviously one should think about.
Yeah, sure. One last question.
So yeah, I have one clear question. So I see like you are using temporal robustness and like multiple agents on environmental sciences especially. What will happen if my ego, like you're talking about an autonomous vehicle, right? So in case of ego vehicle, like suppose you're making a you're supposed to have the bigger speed, bigger frictions, or and your bigger force on your like natural acceleration and whatever that is, right? That's also this sensitive thing, right? We don't want to turn at like over. We don't have to turn on over speed. So is it possible to formulate those problems also in a temporal robustness form? If yes, then how we can verify it? Because
Can you maybe formulate it again? I didn't fully get the question.
I'm saying, like, can we like when only my agent like the ego vehicle is going into like driving in a environment, and when you are making a turn, like a turn, you have to be careful about lateral acceleration, how much acceleration you are getting, and all.
Yeah.
Like, it's a risk sensitive, right? So is it possible that this problem also can be formulated in terms of temporal robustness forms that can be evaluated? And like addition of this question, if yes, then how we can verify, how we can say that okay, temporal robustness works there, because you can't collect those data there, right? You can't like turn on like so pretty.
I think what this relates to is kind of the modeling, I'd say, right? I mean, if you're talking about friction or something like that, it relates to the model of the system, not necessarily to the specification and the temporal robustness. So I would say, yes, you can incorporate that by simply incorporating it in the model, right? So if you have uncertainty in your friction, you can simulate that to some extent, and you can see what effect this has on the temporal robustness of your system, right? If you increase the friction, does my temporal robustness get better or not? Or, these kind of effects will simply show up with respect to the specification that you have chosen.
Yes, so basically my question was like, since here you formulated because you have multiple agents for like kind of flat time. So what will happen when you have only single agent?
Yeah. You can also use the temporal robustness. Yeah, I was just more the multi-agent thing. I was just using it as a motivation for where, in my opinion, temporal robustness really matters, right? So if you have multiple agents involved, but clearly it also matters in some single agent systems, let's say. I mean, deadlines, for instance, are something for, I want to go from A to B in a certain time. You can define temporal robustness for that. If it's really relevant for such a simple task, it's a different thing, but it's just one example. And then in your driving scenario as well, right? I'm not a specialist with driving, how like I guess it involves, but thank you.
So we still have one session of posters and then one last talk. Most of the posters, well, all the posters in this session are virtual, so we're just gonna go ahead and get started with that. Sarah, how was you? Just,
I'm
yeah.
with it.